Hello everyone. The last video we have seen the definition of vector spaces and some examples like set of all real numbers, set of all ordered n tuples, how they become a vector space, and some examples we have written directly that they are vector spaces, and those examples were left on you to verify that really they are vector spaces or not. Okay. So before uh, continuing further in this video, I suggest you to watch the previous videos again just to revise all those things. Okay, so we are going to prove the first theorem of this unit. I have already written the statement here. Let V be the vector space over a field F, then alpha into 0 is equals to 0 for all scalars. Similarly, 0 into v is equals to 0 for all vectors. Next, minus alpha into v is equals to minus of alpha into v for all scalars alpha, and for all vectors v, alpha into v is equals to 0 if and only if either alpha is 0 or v is equals to 0. Okay. Next, the distributive property, alpha into u minus v is equals to alpha into u minus alpha into v, true for all vectors and scalars alpha. And last, minus 1 into u is equals to minus u. Okay, so let us prove number one first. So let v be the vector space over a field f. Okay, so number one, claim what we have to prove: alpha into 0 is equals to 0 for all scalars alpha of f. Okay, so we have, since 0 is the identity element of v, we have 0 the identity element of v, then 0 plus 0 is equals to 0, we can write. And now for say scalar alpha, we multiply this equation from left hand side, and what that called, the post multiplication, sorry, pre multiplication. Okay, so pre multiplying this equation by alpha, what we get: alpha into 0 plus 0 is equals to 0. And then by distributive property, in the definition of vector spaces, we get alpha into 0 plus alpha into 0 is equals to 0 by distributive property. You don't write dp there in your notes. Okay, you write fully distributive property by distributive property. So next, I haven't multiplied alpha on right hand side, so there it is, alpha alpha. Okay, so now as 0 is identity element, we can add that identity element on right hand side. So alpha into 0 is equals to alpha into 0 plus 0. 0 belongs to v. Okay, so by right cancellation law, this alpha 0 and this alpha 0 will get cancelled, and we will get alpha into 0 is equals to 0. Thus for all alpha belongs to f, we have alpha into 0 is equals to 0. Simple. So let's prove next. Number 2, claim what we have to prove: 0 into v is equals to 0 for all vectors v. So we go similar way. So we have 0 belongs to f. Since f is a field, so 0 is the additive identity of f. So then we can have 0 plus 0 is equals to 0. Here we are taking 0 from f. Okay. So for vector v of v, here what we need, v on right hand side. So we post multiply this equation by vector v. So 0 plus 0 into v is equals to 0 into v. Okay. So again by distributive properties, we get 0 into v plus 0 into v is equals to 0 into v. So now this is the element of vector space v by scalar multiplication. Okay. So we can add the identity element of vector space v on right hand side. So 0 into v plus 0 into v is equals to 0 into v plus 0 for 0 belongs to vector space v. So again by right cancellation law, we get 0 into v is equals to 0. Thus for all vectors v of v, we have 0 into v is equals to 0. Simple. So next number we will prove now. Number 3. Claim minus alpha into v is minus alpha into v equals to minus alpha into v for all alpha belongs to field f and for all v belongs to v. Okay. You have seen this many times. Minus alpha into v is equals to minus of alpha into v. That means we have to prove minus alpha into v is the additive inverse of alpha into v, because what it is, alpha sorry minus into alpha into v. Okay, I am repeating again, what it is, minus of alpha into v, and minus of any element is nothing but the additive inverse of the element. Okay, so proving this equation means we have to prove minus alpha into v is the additive inverse of alpha into v. So let us start. We write that here. We prove minus alpha into v is additive inverse of alpha into v. Okay, that is minus alpha into v plus alpha into v is equals to 0 for all alpha belongs to f and for all v belongs to v. Clear? So now for alpha belongs to f, we take or we have, as f is a field, minus alpha will be there in f, so that alpha plus minus alpha is equals to the identity element, that is 0. Okay, so here we post multiply this equation by V. So for V belongs to V, post multiplying this equation by V, 0 into V. So by distributive properties, we get this as alpha into V plus minus alpha into V is equals to 0 into V from previous equations, previous proofs. This number 2, 0 into V is equals to 0. We have proved this just before this number. So 0 into V is 0. Give reason here by distributive property, and by number 2 we have proved. So this is alpha into V or alpha V plus minus alpha into V is equals to 0. That means this quantity, that is minus alpha V is sorry minus alpha into V is the negative of alpha into V, or you can say minus alpha into V is the additive inverse of alpha into V. Okay, because their sum is equals to the identity. Hope this is clear to you. So in the end you can write thus minus alpha into V is equals to minus of alpha into V for all alpha belongs to F and for all vectors V belongs to V. Okay, so next number 4, claim alpha into V is equals to 0 if and only if alpha is equals to 0 or V is equals to 0. Okay, where alpha is from F and V from the vector space V. Okay, so let alpha belongs to F and V belongs to V. So here we have to prove this equation if and only if alpha is equals to 0 or V is equals to 0. So we will have two part here. In first part we will assume this and prove this, and in second part we assume this and we will prove this. Okay, so let us take this part as a given in first case. Okay, so let alpha equals to 0 or V is equals to 0. We have to prove alpha into V is equals to 0. If alpha is equals to 0, then alpha into V will be 0 into V, and we have proved in the number 2 0 into V is equals to 0 by 2. If V is equals to 0, because or is there, that is why we are writing this. So if V is equals to 0, then alpha into V will be alpha into 0, and in number 1 we have proved alpha into 0 is equals to 0. So in the both cases, even if alpha is equals to 0 or V is equals to 0, we are getting the product of alpha into V is equals to 0. So we have proved the first part. Now we go for converse. Conversely, now we assume alpha into V is equals to 0, and we will prove either alpha is 0 or V is 0. Say In this case, if alpha is equals to 0, we will have nothing to prove because 0 into b is already proven to be 0. Okay, so we assume alpha is not 0. So we must get, if alpha is not 0, v is equals to 0. Okay, so if alpha is equals to 0, then we have nothing to prove. Okay, so assume alpha is not equals to 0. So if alpha is non-zero, then inverse of alpha, specifically multiplicative inverse of alpha, will exist as alpha belongs to the field F. Okay, so we assume alpha not equals to 0, then multiplicative inverse of alpha, that is alpha inverse, exists since alpha belongs to field F. Okay, next, so next, what will we write now? As we are given alpha into v is equals to 0, alpha into v is equals to 0 given. Okay, we will pre-multiply this equation by alpha inverse. Okay, pre-multiply by alpha inverse, we'll get alpha inverse into v is equals to alpha inverse into 0, which will be, by associative properties, alpha inverse into alpha v is equals to, and alpha inverse into 0 will be 0, uh, and alpha inverse into alpha will be the identity 1, because alpha inverse is the multiplicative inverse of alpha, so identity must be 1. So 1 into v is equals to 0. You can give reason here by associative property. Okay, and we have used number 1 on right hand side and by 1. Okay, so 1 into v is equals to 0, and we have uh, 1 into v is equals to v in v3 in the definition of vector space. So this is equals to v equals to 0. Okay, you can write by v3, the third condition of vector space, particularly the last condition of v3. Okay, because in v3 we have proved the four sorry, we have 4 points, we didn't prove those four, as it's a definition. Okay, so where we have started, we have started uh, assuming alpha is non-zero. If alpha is non-zero, we have reached where v is equals to 0. Okay, similarly we can prove if v is non-zero, then alpha is equals to 0. Okay, so whenever alpha into v is equals to 0, either alpha is 0 or v is equals to 0. We will write that here. So thus alpha into v is equals to 0 if and only if either alpha is 0 or v is equals to 0. Okay, next, number 5, I think. Yes, number 5. What we have to prove here? Alpha, claim alpha into u minus v is equals to alpha into u minus alpha into, these are the distributive properties, distributivity. you can say for all alpha belongs to field F and for all vectors V of V. Okay, so consider U minus V. This can be written as U plus, sorry, I have written alpha U minus V. So U, this can be written as U plus minus V. Okay, next we need alpha from the left hand side. So pre-multiplying by alpha, we get alpha into U minus V equals to alpha into U plus minus V for alpha belongs to field F, and that from distributive properties you will get this as alpha into U plus alpha into minus V. Okay, by distributive properties. Next, this is nothing but alpha U minus or plus minus alpha into V. Okay, or alpha into U minus alpha into V. Okay, so this is very simple. You follow the left hand side, alpha into U minus V. So number 5 is proved. Now we move to number 6. What we have to prove? That minus 1 into U is equals to minus U for all vectors U of V. See, we have already number 3. Let me show you this. Number 3, minus alpha into V is equals to minus of alpha into V. If you put alpha is equals to 1 here, you will get minus 1 into V is equals to minus of 1 into V, that is again V. So now your number 6 will be proved automatically. Okay, or if the question is asked without asking that number 3, then you have to prove this manually. Okay, so we'll prove this manually, like we have proved number 3. So let U belongs to V, then we have minus U belongs to V. Okay, such that U plus minus V, sorry, U plus minus U is equals to the identity 0, the inverse property. Next, what we need, we multiply uh, pre-multiplying this equation by minus 1. So we write minus 1 into U plus minus U is equals to minus 1 into 0. Okay, so this is minus 1 into U plus minus 1 into minus U is equals to minus 1 into 0 will be 0. Okay, so minus 1 into U plus U is equals to 0. Okay, so this equation means minus 1 into U is the additive inverse of U. that is minus 1 into u is the additive inverse of u. Okay, that is what we wanted to prove. Thus minus 1 into u is equals to minus u for all u belongs to the vector space V. So hope this full proof is clear to you. If you have any doubt, you ask in the classroom, you write there. I will try to solve your doubts. Okay, so this is all for this video. I will cover the further topics in this unit in the next video. Okay, thank you.